All right, so 4.4, looking at radical functions. So radical functions are basically things that have like roots in them. There's a pretty big difference between even roots and odd roots. We're going to look at what the differences are. The example on the left, that's a pretty typical example. We're going to talk about what this minus 2 would do. Cause some type of shift to the graph. So we'll look at transformations, we're going to look at sketching, and we'll look at solving equations. Those are the three things. Now when you write a radical expression, there's different names for each thing. So any expression that has a root in it and something under the root is called a radical expression. So any expression that has some kind of root and then something under it is called a radical expression. Now, this number that's on the outside is called the index. And it tells you what kind of root you're doing. It could be cube root, fourth root. The index has to be an integer. It could be 2, 3, 4, 5, and it has to be bigger than 1. So no decimals for the index. No negatives. It's got to be higher than 1. So the number that you put there is called the index. What's underneath, that's called the radicand. So I get that example up above on the left. X minus 2 is the radicand. On the one on the right, x squared minus 1 is the radicand. The actual thing that you draw when you're making that symbol, that's just called the radical sign. So you got the radical sign, the index, the radicand, and the whole thing is called a radical expression. Okay, any questions on any of those terms? All right. If you don't put a, like in the first example, I didn't write an index. In the second one, I put an index of 3. What do you always assume the index is if you don't write one? Yep.
2.
Yeah, we always assume it's a 2. A little weird. Usually in math, we kind of assume things are 1s if we don't write them. Like if you just write x plus 3 and I ask what number is in front of x, it's like having a 1. We assume it's a 2. Now, radical expressions can also be written with exponents that are fractions. Does anybody know what exponent you can use? And if you raise something to this power, it's the same thing as doing a square root. Yep.
The half power.
Exactly. If you raise something to the half power, you can try it on the calculator. Take 16 and raise it to the 1/2 power. You will get 4. Now, if square root is the same as to the 1/2 power, what do you think cube root would be? If you want to do a cube root, you could raise it to the 1/3 power. Yep. In general, it's 1 over the index. If you're taking a 50th root, raise it to the 1/50th power. How about if we were doing a 5th root? What power would we use for that? Yeah. Okay. We'd use 1/5. And this is an example where it simplifies. Because when you take x to the 4th and raise it to the 1/5, you have a power to a power. What do you do when you raise one power to another power? Yeah. Multiply. And what's 4 times 1/5? 4/5. So that's where this can kind of come in handy. It can help you to simplify something like that. So any questions on the exponents you can use to replace writing a radical sign? Okay. So when you take a square root, let's say I asked you for the square root of 25. What do you get? Square root of 25. Yeah?
5. Square root of 25.
Square root of 25, yeah.
It's 5, right?
Yeah, partially. Yeah?
Plus or minus 5?
Plus or minus 5. So there's two answers. So when I ask you specifically for what's called the principal root, I only want one answer. Now, we have to break it into two cases. We have to break it into the case where we're doing an odd root versus an even root. If you're dealing with an odd root, you're basically trying to solve that equation, where n is the index and a is the radicand. Let me show you what I mean. Let's say I asked someone to find the cube root of 64. And they said, I have no idea what cube root means. What does that mean? I'd say, okay, that means there's a number you can raise to the third power, and it will come out to 64. If you can find the number that you raised to the third power to get 64, then you just found the cube root of 64. Right? So that's basically what you're doing to find an odd root. What number do you raise to that power to get that number? And in this case, what can you cube and get 64? Bruce?
4.
4, yeah. And that's it. That's the answer. Now, if it wasn't 64, let's say it was x cubed equals 60, well, now you have to take the cube root of 60. Not as easy to do, but we use a calculator. To do a cube root, you press math, and then you press option 4. That's one way to do a cube root. And then you just type in whatever you want. With odd roots, there is no restriction on that radicand. You can take the cube root of an odd number. Well, I shouldn't say it that way. You can take the cube root of a positive number or a negative number. Doesn't matter. Right. If you take the cube root of, let's do cube root of negative 125. You get negative 5. So with odd roots, you can get negative answers or positive answers. Any question on that? No. Let's look at even roots. With even roots, we got to be a little bit more careful about what we put as the radicand. Why did I say this? Why does the radicand have to be greater than or equal to 0 when you're doing even roots? Yeah?
Because you can't take an even root of a negative.
Okay, you can't take the even root of a negative under what kind of number system? Because technically you can do that, but yeah, right. You can't take an even root under the real number system. You can under the imaginaries, but we're dealing with real numbers, so we don't ever want what's under the root to be a negative if you're doing an even root. It has to be 0 or higher. 0 is okay. You can take the square root of 0 and just get 0. And remember the question I asked earlier about square roots. I said, what's the square root of 25? There were two answers. If I ask for the principal root, I want that answer, the non-negative one. So in the case of square root of 25, I'd be looking for 5. You will never get a negative answer when you do an even root. Won't happen. Well, the principal root. You'll never get a negative answer for the principal root. Any questions on that? All right, now what I want to look at is what happens when you take a square root. I want to see if it gets smaller or larger. You see what I did there with the font? So smaller is smaller, and then larger is larger. Pretty good for it. Yeah. All right. So we have x, and then we have the square root of x. When you take the square root of 4, what do you get? So what happened? Smaller or larger? Okay. So you took the square root, it got smaller. The square root of 18. Well, it's 3 square roots of 2, but we're trying to just do it as a decimal. So square root of 18, about 4.2 maybe? About 4.2. Okay. Smaller or larger? Got smaller again. So it looks like when you take square roots, it gets smaller. How about the square root of 1? Yeah, 1. Well, that didn't get smaller. So maybe when you take square roots, it either stays the same or gets smaller. Let's try this one. The square root of 0.5. 0.71. So what happened that time? It got bigger. So whether or not, when you take a square root, the answer to the question, does it get smaller or larger? It depends. What do you think it depends on? If the number is this, then this will happen. Or if it's this, then that'll happen. Yeah?
If it's 1 or above, it's going to get smaller. Well,
If it's above,
yeah.
it'll get smaller. Yeah. If it's below 1, it gets larger.
Yes.
And if it's exactly 1, it stays the same. Yeah. And the square root of 0, that stays the same too. So we should mention that. All right, so let's keep that in mind. And let's graph all of these roots. Now, if you press math, there is not a button for every single root. You have square root, you have cube root, and then you have the x root. So we're going to have to use option 5 to type those in. So let's put in square root of x. And the way you do the 4th root is you press the index, then you press math, and then option 5. And it'll change the number you put in to be the index in the root. So 4th root of x, and now we'll do the 6th root. So 6, math, 5. So I'm going to graph all 3 of these. I just want to kind of see if they have anything in common. They're all even roots. And I'm going to do zoom 6. So first thing, what do you notice about all those roots? Do they all have anything in common? Yeah.
They all started at the origin of 0, 0.
They all start at the origin. Yep. Anything else? Yep.
They're all in the first quadrant.
Yeah, they're all in the first quadrant. So let's zoom in there. Let's set our y max at maybe 3 so we can see it better. They don't go into quadrant 4. They don't go into quadrants 2 and 3 either. Okay, so there's your square root. There's your 4th root. And then coming up next will be the 6th root. All right, so I'll take that, make it so we can see a little better. And we did say, I think they all start at the origin, so we got that. Is there any other point they all have in common besides 0, 0? Yep.
They look like they intersect at 1, 1-ish.
Yeah, they do all intersect at 1, 1. 0, 0, and 1, 1 are common to all of them. Now, we said that they are in quadrant 1. So let's kind of go with that a little bit more. What does that mean about the domain then? The domain here is from what to what? Yeah? The domain is 0 to positive infinity. And what about the range?
0 to positive.
It's also 0 to positive infinity. Now, which graph is above all the other graphs? Yeah?
Square root of x.
The square root of x is always above the other graphs?
Not always.
Not always. So what do you mean?
I mean, starts at the bottom, but then it is at top at the end, I guess.
And where does it kind of switch places?
Where they all intersect.
And that's at the number
One.
1. So we talked earlier about whether does it get smaller or does it get larger, and 1 was kind of the point where it changed. All these graphs change places at 1. If you go after 1, the square root is above everything. If you go before 1, it's below everything. So let's write all that down. So 0, 0, and 1, 1, common points. The domain and the range, it's limited to the first quadrant, so 0 to infinity. And if you're in, let's go like this. Okay, if you're in that strip right there, that's the 0 to 1 strip. Then, well, now I changed the color, so that doesn't look good. If you're in that strip that I highlighted, then what ends up happening is the lower the index, the lower the graph will be compared to other ones. So the square root is under the 4th root, which is under the 6th root, which would be under the 8th root. When you go after the number 1, all of that switches. The lower you make the index after the number 1, the higher the root is. So the square root has the lowest index, but it's the highest. The 6th root has the highest index, but it's the lowest. So that's kind of the behavior of even roots. Any questions about any of those facts that we just wrote down about even roots? Because now we're going to do the same thing for odd roots. All right, let's try graphing the 3rd root and the 5th root. And you could throw the 7th root in, but it just starts to get kind of too much on the screen. So I think if I already have these roots typed in, I can actually just highlight the index and just change the 4 to a 3 and change the 6 to a 5. If you don't have them typed in and you cleared it, you just type it all in again from scratch. So 3rd root, 5th root. Let's do zoom 6. What's one big difference that you can notice right away looking at the graph of an odd root? Yeah.
It's in the negatives.
Yeah, it goes in both directions. Right? When we talked about taking odd roots, I told you can take the odd root of any number you want. Positive number or a negative number. Okay. Now, another thing I want to do is try to, let's go like -2 to 2. Let's go -4 to 4. I really want to zoom in kind of towards the origin and see what's going on. Okay, so there's your cube root. It is connected. I know it looks like there's a little gap. There shouldn't be. It's connected. All right, and that shows it pretty good. Let's look at that. Do these graphs have any points in common? Yeah.
It also has -1 and -1.
-1, -1. Yep. That's fine. That's a point. What else? Yep. 1, 1. And I know it's a little hard to see, but what else? Yeah.
0, 0.
Yeah, they all go through 0, 0. The problem is it gets almost vertical, so it has a problem. So they have all those points in common. So you can see them okay. And then it goes in both directions. And then which graph is above the other graph, or does it depend? What do you think? Is like the cube root always above the 5th root, or vice versa, or does it depend? Riley, what do you think?
I think it depends. It changes.
Yeah, it changes. Sometimes the red one is on top. Well, there's two sections where the red is above the black, and then there's two sections where the black is above the red. So there's really four sections here. Less than -1, between -1 and 0, between 0 and 1, and more than 1. So we'll kind of summarize that. What about domain and range? What's domain and range here? Yeah.
All real numbers.
Yeah, they're both all real numbers. Yep. So those 3 points are common to all the graphs. Now, when I say they're common, I mean if you don't shift it. If you take these graphs and shift them all left 2, well, then all the points that are common are going to shift left 2. Right? But if you don't shift it, those are the points they have in common. Domain and range is all real numbers. And then if you are less than -1 or between 0 and 1, the lower you make the index, the lower the graph will be. In those two sections, cube root is a lower index than fifth root, and it would be under on the graph. In the other sections, it reverses. So when you go between -1 and 0, or more than 1, the lower you make the index, the higher it's going to be. So cube root is a lower index, but it's higher than the fifth root. Right, so it just kind of describes what's happening. There's a pretty big difference when we draw a cubic versus when we draw an odd versus an even. Okay, questions on? Okay, so transformations. Let me copy that down so I have a little bit more space to write. Okay, so C dx plus A. And did I use D? Yep. Okay. The A, the B, the C, and the D all do something to the graph. A and the B are on the inside. C and D are outside. Does anyone remember what adding inside the function would do? Yeah.
Move to the left.
Yeah, or move it to the right, and those are examples of horizontal shifts. Yeah. I did ask a very specific question, and you answered it correctly. But in general, yes, adding or subtracting inside is a horizontal shift. Positive moves it left, negative right. What about B? It's still inside, but it's multiplying instead of adding. So multiplying is always what kind of transformation? It's not the shift, it's the stretch. And since it's inside, it's the horizontal. And just like the shift, it is backwards. So if you had something like this, I would say that is a horizontal, you could say it two ways. You could say horizontal compression by 3. Or you could say horizontal stretch by 1/3. You could say it either way. But the bigger you make this number, the more compressed the graph gets. The smaller you make this number, the more stretched it gets. So if you did like square root of 1/2x, that's a small number. That small number is going to stretch it bigger. You could either say it's a horizontal stretch by 2. That's what's really going to happen in this one. It's going to stretch it by 2. I mean, I guess you could say it compresses by a half, but now that's a double negative. You're compressing by a half, which really means you're stretching. I think it's confusing to say it that way. Okay, so the important thing to remember, the bigger you make this number, the more it compresses. The smaller, the more it stretches. Okay, what about C? That's multiplication like B, but it's outside. Yep.
It's a vertical stretch.
That's a vertical stretch. Nothing backwards about that. The bigger you make it, the bigger it stretches. The smaller you make it, the more it compresses. And what about D? Yeah,
Vertical shift.
that's a vertical shift. And again, nothing backwards with it. Plus is up, minus is down. B and C are the only backwards ones. Now, what if B or C is a negative? Anyone remember what that causes the graph to do?
Is it a reflection?
It's a reflection. If B is negative, it's a horizontal reflection. If C is negative, it's a vertical reflection. Okay, so just remember, vertical reflection would mean this. A vertical reflection is really a flip over the x-axis. A horizontal reflection, that's a flip over the y-axis. You can say it either way, horizontal reflection or reflect over the y-axis. Okay, but that's the chart, and it's the same kind of thing we've done before. That's what I just said to you. So it's exactly the same as the transformations we've studied before. All right, so here's a function. Here's what I want you to compare it to. And I just want to know what transformation is taking place there. If there's only one transformation, you don't have to worry about any order. You just write it down. If there's more than one, follow the order A, B, C, then D. Okay. So what's the transformation that's happening there? Yeah.
It's a horizontal shift to the right.
That's going to shift to the right. You just tell me a little
By
bit more.
2.
By 2. Yeah. So shift right 2. All right. Let's try this one. Square root of x plus 3. Compared to square root of x, what's x plus 3 doing? Yeah.
Shift left 3.
So shift left 3. Now this one isn't written in the format that I showed you. It's not written like that. But you can make it written like that if you want. How could you fix this so the pattern there lines up with what I showed you? Yeah. Hey, you could make it the square root of negative x plus 3. I don't care if you really do that, because all I'm interested in here is if you can tell me those two things in the right order. Okay, so what's the first thing that would happen to that graph? Yeah.
So shift left 2.
Can you say it again?
Oh, 3, sorry.
Yeah. So shift left 3. And the last thing that's going to happen.
Reflection?
What kind?
Horizontal.
Horizontal. And horizontal reflection means over the y-axis. Now, what if you had this? Let's say 2 square root x minus 4, and it had a plus sign there. I know the minus 4 is shifting it to the right 4, but what's that 2 plus in the front going to do? Is that a vertical stretch because it's in the front? What do you think?
Maybe a vertical shift.
Yeah. That's a vertical shift up too. What I would do is if it confuses you like that, then rewrite it so it matches the pattern that I showed you. Any adding or subtracting outside the root is a vertical shift. I don't care if you add it in the front or you add it at the end. It's still a vertical shift. All right. Any questions on the transformations? All right. So, when we did even roots, what was one of the points that was common to all of them? Yeah. Yeah, 0, 0. Let's focus on that one. 0, 0 is where it starts. Okay, so I call this the start. In an even root, that's like your 0, 0. I don't call it a start because it goes left and right. I call this the center point. Either way, if we do a transformation, shifting and stretching, we need to find the new location of that point, whether it's the start or the center. You find it the same way. Okay, so we're going to look at how do we find where that point ends up. For even roots, it's a start. For odd roots, it's a center. So that's an important point that you want to plot anytime you're doing a sketch. The start or the center. Well, that point is going to move depending on how you shift or stretch your graph. To figure out where it moves to, you have to find two things. The x value could move somewhere, and the y value could move. To find where the x value is going to move, take what's under the root and set it equal to 0. That will tell you where the x value goes. So we got something like that. You would set 2x plus 4 equal to 0 and solve. Once you solve that, you're going to get an answer. In this case, you would get -2. Yeah, -2. Once you know that x is -2, you can substitute -2 back in for x and then solve for the new y value. But you're going to notice when you plug in -2, a big part of that is just going to be 0. And there's only really one thing that's going to matter when you substitute back in for x. Now, that's just one point. It's not the whole graph. That gives you the start or the center. From there, we're going to check some other points. If it's an odd root, then you have to check points to the left and the right. You got to check both sides because the graph goes both ways. If it's an even root, you don't need to check both sides. In fact, you can't. If you're graphing an even root and you try to plot points in the direction the graph doesn't go, you're going to get imaginary answers. Okay? So with even roots, we only have to plot points on one side of the start. Odd roots, you got to do both. And the easiest way to plot these points is use the table, and then you can get them real quick. If you don't have a graphing calculator, you can do it by hand, but you're going to have to plug every point in one at a time. And it's going to take a while. So I would advise you to use the table. And make sure you set it up so it's on ask, and then you can type in whatever you want. Okay, so let's sketch this one. First of all, is this graph going to have a center or a start? Yeah.
Center.
It's going to have a center. So when we're done, center's a little bit more work because you got to check like 2 or 3 points on one side and then plot 2 or 3 points on the other side. Okay. What am I going to set equal to 0 to find the new x value of the center?
Graphing.
Yeah, which is 3 minus 2x. There you go. So x is 3 halves. If you're graphing it, maybe 1.5 is easier to think about. So x is 3 halves. And y, well, take the x value and plug it back in. What's 2 times 3 halves? Yep. 3. And what's 3 minus 3? Yeah, better be 0. So we have 0. And what's the cube root of 0? 0. And what's 0 times 2?
0.
Still 0. Plus 1? 1. So that plus 1, that's really the only number that affects the y value of the center point. All right, so now we've got that. So let's get a graph here. Let me try again. Graph. There you go. Down there. Let me get rid of those other points so we don't get confused with those. Okay, so the center is at 1.51. And because it's a center, I'm going to check a few points on each side. Okay, so let's type in 2 times the cube root of 3 minus 2x plus 1. So 2 times the cube root of 3 minus 2x, and then plus 1. Is there any question on how to type in what I just typed in? Okay. So go to your table. If you're not on Ask, put it on Ask. Let's check the center. 3 halves, comma 1. Perfect. So that's great. What would be a couple values? Let's do 3 values to the right of the center. 3 x values right of center. Bruce?
2.
Okay. You have another one?
Yeah.
Yeah.
3.
Okay, let's not bunch them too close together. Let's spread them out over that whole area.
6.
Yep, 6 and
4.
yeah, we already have 2 and 6, so we can kind of estimate what's between. Let's go beyond 6.
How do I say task again?
Second window. I just picked some. Just don't pick them too close together. Space them out so you get a decent graph. And let's see what it looks like. So we got 2, -1. We've got 6, a little past -3. And then 10, a little after -4. So there's one side. 0, 3.8. Right there. -2, just below 5. And then -8, just after 6. That's pretty good. I mean, maybe you want one more in there, but I think we got enough points we can kind of sketch this. And there's your graph. Okay, any question on sketching a cubic? That's it. Okay, I'm not going to to skip this one, but I'm just going to ask a few questions about it. Is this graph going to have a center point or a start point? Yeah? Yep, it's going to have a start. And an even root normally curves which way if you don't transform it? Yep.
Right.
Normally curves to the right. This one has a horizontal reflection. So which way is it going to curve? Yeah.
It's gonna curve left.
Yeah, it's going to curve left. That means once you find the start point, you are only checking x values below it. If you try to plug in an x value above it into your table, it's going to say error because it doesn't curve to the right. And it'll say error because the answer would be imaginary. So any question on that? Okay, so that's schedule. And the last thing. So solving equations. So the goal when you're trying to solve an equation that has a radical in it, you have to get the radical by itself and then raise each side to the power of the radical. So if you had a square root, you are going to square each side, and that'll get rid of it. If you had a cube root, you're going to cube each side. Sometimes you have to do it twice. You'll know when you have to do it twice. We're going to try ones where you only have to do it once, and then we'll maybe finish with one like that. You do want to check for extraneous solutions, because if I gave you a problem like this, when you take the square root of a number, square root always gives you what kind of answer? This is like the principal square root. Yeah? Positive. You're never going to take the square root of something and have it equal negative. It's not going to happen. Even just think about what this would look like as a graph. Here's a square root. Here's -4. Where do those cross? They don't. So the square root of x will never equal -4. Okay, so that, if you try to solve it and you get an answer, well, I don't care what you get, it's not going to work. All right, so let's try one. That was example 5. We kind of skipped it. So I guess this is really example 5. Okay, so the first thing it says to do is to isolate the radical on one side. That means that on one side of the equation, all you have is a radical and nothing else. Is the radical by itself in that one? Do you think that? No. Radical's not by itself. What's there that we don't want there? Yeah. We don't want the +3. So we got to get rid of it. How would you get rid of the +3 and move it to the other side? Yeah. Subtract 3 from both sides. That's always the first step when you're solving a radical equation. Get the radical by itself. Now, raise each side to the power of the index. What index is right there, even though we have it written in? 2. So square each side. When you square a square root, that's gone. And 1 squared gives you 1. And you're done. That's a pretty simple square root. X is 3. You can plug it back in and check it. It works fine. Any question on that one? Okay, so that's kind of like that's the simple. Now we'll try one a little bit harder. Let's try this one. I think it's really example 6. Okay. First question to ask yourself is the radical by itself? Yeah, it's by itself this time. What's the index on that root?
3.
3. So you are going to cube each side. You cube a cube root, that's gone. And when we're trying to solve an equation that has higher powers in it, 2s or 3s, what do we generally try to get on one side? We do it with quadratics all the time. Yeah?
0.
0. Now what I would do is I would move everything to the right side because generally for what we're going to do next, the highest degree term, if it's positive, will make life a little easier. So we have x cubed, and then move everything over. Minus x squared, plus 2x, and then minus 2. All right, so x cubed minus the x squared, add the 2x minus the 2. All right, when you have 4 terms, does anybody remember what kind of factoring you can try? And if this doesn't work, then I don't know how we're going to solve it algebraically. Yeah.
Group factor.
Yeah, we're going to try to factor it by grouping. What can you factor out of the first 2 terms? Yeah. X squared. That's going to leave you with x minus 1. And the goal is to get x minus 1 again. How about, Elizabeth, what can you factor out of the next 2 terms? Yep, you can factor out of 2. And that leaves you with x minus 1. Perfect. So now, look at what I just kind of blocked off there. What can you factor out of each of those? Yeah, let's take out the x minus 1. And Jameson, if I take x minus 1 out of the first one, what's left?
X2 plus 2.
Yeah, x squared. And then if we take it out of the next one, you're left with a plus 2. Now set each of those factors equal to 0. Okay, so we have x equals 1 for the first one. What's going to happen when we try to solve the second one? X squared plus 2 equals 0. Yeah.
You'd end up having a square or negative.
Yeah, you're going to have a square root of a negative. That's imaginary. We're not worried about imaginary answers. So the only answer here is x equals 1. So a little different than the first one because we had to use the factor by grouping to solve it. Any question on that one? All right, now let's try. Let's try this one. You're going to have to do something twice here. Right? However many times you see roots in the problem, that's how many times you're going to have to raise each side to a power to cancel it. So the first step is the same. Isolate the radical. Do we already have a radical by itself here? What do you think, Jake? No. You have to have one radical by itself. Could you tell me something I could do on both sides to get one radical by itself?
Put each side to the power of 2.
That won't isolate a radical. Isolating means you add, subtract, multiply, or divide to get a radical alone.
Add the square root of 4x plus 9 to the other side.
Yes, let's move the square root of 4x plus 9 to the other side. So now you'd have this. And now we have a radical by itself. Now, I can get rid of the radical on the 6x plus 12. What power would I raise each side to do that? Yeah? The what power? Yeah. I'm going to raise each side to the second power. Now, on the left side, you get 6x plus 12. To do the right side correctly, sometimes they use a word to remember how to do it, but there's a method you're going to have to follow on the right side. Anybody know what method I'm thinking of? You don't just square the 1 and then square the square root of 4x plus 9. That's not how you do it at all. Yeah, you have to FOIL that. So if it's easier to see it, then write it like that. That's what you need to do on the right-hand side. Okay, so let's do that and see what happens. Okay, so 1 times 1 gives me 1. 1 times the square root of 4x plus 9 plus another 1 times the square root of 4x plus 9. How many square roots of 4x plus 9 is that? 2. So I have 2 square roots of 4x plus 9. And what's the square root of 4x plus 9 times the square root of 4x plus 9? It's like saying the square root of 4x plus 9 squared. Yeah?
4x plus 9.
4x plus 9. Yep. Okay. Now, what do you think we have to do with that? And we've done this step before when we solve radicals. Yeah?
Isolate it.
Okay, to get it by itself again. So everything that's on that side, that's outside that red box, needs to move to the other side. Let me just make sure we got everything. 1 times 1, 2. Yeah, I think it looks good. All right. So let's start to move things over. What number could I subtract from both sides to put all my constants on the left? Yeah?
12.
What do you get if you add all the constants that are on the right?
12, I think, right? Not including ones in the square root.
Tell me, what are your constants?
We have 9,
9 is a constant, yep.
1. Oh, 2's multiplication.
Yeah, the 2 is multiplication. That's not a constant. Yeah.
So it would be 10.
That's 10. So you have a 10 on the right. So subtract 10 from both sides. That's gone. That's gone. Okay. Anything else I can move to the other side in this step? Yeah.
4x.
We can move the 4x. So that's gone. And now it's going to look a lot simpler. We've got 2x. 12 minus 10 gives me 2. Constant's gone. Constant's gone. The x is gone. And we have 2 square roots of 4x plus 9. What would be my next step to isolate the square root? Sophia?
Can you divide by 2?
You have to. You're going to divide everything by 2. That's gone. That becomes 1. That becomes 1. So now we've got x plus 1 equals the square root of 4x plus 9. Now it's starting to get into a much simpler problem. What do I do on both sides now to get rid of that square root? Yeah. Square it. So square this. Square this. Now all your square roots are gone. You have 4x plus 9 on the right. X squared plus 2x plus 1 on the left. Okay, and that's a quadratic equation. So what do we want to get on one side by itself? 0. So let's bring the 4x over, bring the 9 over, and that's going to give you x squared minus 2x, 1 minus 9, negative 8. I'm just saying for factorable. We can try. If I'm going to try to factor it, what would be my first term in each parenthesis? X. What would my signs be? It would have to be a plus and a minus, and two numbers that multiply to give me 8. 4 and 2. I think it might work. So that gives you x squared minus 2x plus 4x minus 2 plus 4. Oh, no. So what do I have to do? Switch the signs. Plus, let's try it again. 2x minus 4x is negative 2x. That's good. So what are the two numbers that would make those factors 0?
Yep. 4 and negative 2.
4 and negative 2. Now, if I go back up and try them, let's start with the 4. What's 6 times 4? 24 plus 12. And the square root of 36? 6. Okay. And 4 times 4? And 16 plus 9? And the square root of 25? And does 6 minus 5 give me 1? Perfect. So that works. And negative 2. Well, let's see. What's 6 times negative 2?
12.
And then plus 12?
0.
Square root of 0? 0 minus. This isn't looking good. So let's try negative 2. What's 4 times negative 2? Negative 8 plus 9? 1. What's the square root of 1? 1 is 0 minus 1. 1.
No.
So that answer is extremeness. So x equals 4 is the only answer. Okay, so that's the hard one. Because you gotta square it twice and then you end up having a factor. But you'll definitely have some of the easier ones on the test and homework as well. Any questions on it? So that finishes up chapter 4. Okay, so that's the homework on 255. Okay, so we'll take a look at that tomorrow. I think there might be one on the homework where it's an inequality. You can use the graphing calculator just like we always do to solve inequalities. It's no different than the kind we did yesterday.